Hey everybody, I'm back. I am going to do a tougher example on the radius of convergence. So here I've got the series of -1 to the n, x plus 2 to the n, all over n to the 2n. So I've just taken a little bit of a head start and I've rewritten it like this. Right, this works because I'm just bringing the n over, and of course x plus 2 to the n over 2 to the n, well, that's the same thing as that whole thing to the n. So this example, you could actually use ratio test, but I'm going to use something else just to show you that it's not always ratio test. But let's get an idea of how this series might work. If I plug in, so it kind of looks like a geometric series, but if I plug in, say, a value like 4, right, so let's say x is equal to 4, then I'm going to get n equals 1 to infinity, -1 to the n, over n times, well, 4 plus 2 is 6, divided by 2 is 3. So it's 3 to the n. Alright, and if you take n to go to infinity, this thing is going to bounce back and forth between -infinity and infinity. So here, I'll show you. If I take the limit as n goes to infinity of 3 to the n over n, well, the top goes to infinity, right? 3 to the infinity is infinity. The bottom, well, it's just n, so it'll go to infinity. I can use L'Hopital's rule. L'Hopital's rule tells me that the derivative of 3 to the n is, well, it's 3 to the n ln 3. If you don't remember this, that's okay. Just imagine if I had e to the n, right? So it's e to the n ln e, and that's why the ln e disappears. Ln e is just 1. So it's just e to the n. That's why the derivative of e to the n is just e to the n. That's kind of off topic though, and the derivative of n is 1. So now I just have, if I take the take n to infinity of the top here, the bottom no longer depends on n, so this is just simply infinity. Right, so that's what happens when I deal with everything except the -1 to the n. Well, if I had the -1 to the n, then I would just be bouncing back and forth because my terms alternate between infinity and -infinity. So just pictorially, you can imagine it's like, well, if I plug in 1, then it would be 3. So I don't know, let's just start somewhere positive. So it just gets bigger and bigger and bigger as time goes on. Anyway, the point is something like this will still not converge. So this is like a function, but imagine the terms in your series are just like points on here. So anyway, the point is, if I plug in something like 3, it's not going to converge. Sorry, if I plug in something like 4, I get back 3 here, it's not going to converge. So you can pretty much imagine that whatever is inside here is going to have to be less than 1, right? If I plug in, say, 5, it's not going to work. If I plug in 10, again, not going to work. Same with the negative values, right? So this works almost like a geometric series. So in other words, you're going to have to deal with the same thing, needing x plus 2 over 2 less than 1. Okay, so just keep that in mind, and that's what we're going to need to work with. It's not that surprising because it does look like a geometric series. So right now, we're going to try to use the direct comparison test. So you remember, in the direct comparison test, everything needs to be positive, right? Like all the terms that you add have to be positive. So we're going to look instead at the sum of n equals 1 to infinity of this whole thing, but taking the absolute value. To the n, and of course, this just leaves me with n equals 1 to infinity of, I'm keeping the absolute value sign, and I guess if we were in class I would ask you why we keep the absolute value sign, but I can't hear you and you can only hear me, so I guess I just have to tell you. So the deal is, if, let's say I pick something negative for x here, something like -3. It has to be big enough on the negative side. But anyway, so if I pick -3 here, I'm going to have -3 plus 2, so it'd be -12 to the n, and that would alternate sign. So that's no good. I don't want that. So that's why I still need the absolute value signs here. I hope it's abundantly clear why we can get rid of the negative 1 to the n. But the point is, I still need the absolute value signs in case this term here gives me something negative every once in a while. By every once in a while, I mean every other term as long as this is negative. Anyway, so let's take a look at this. So I want to use the direct comparison test. Right, so let's start off with what I have. I know this is always going to be bigger than 0. Fair enough, right? I mean, it's got an absolute value sign around it. Of course, it's going to be bigger than 0. Anyway, so now, oh, hey, I just got an email. Sorry. Anyway, I'm going to keep going because I don't want to do this again for the 15th time. So this is less than, what I can claim this is less than is, in fact, the absolute value sign of x plus 2 over 2 to the n. Yes, this is a little bit redundant. In fact, you could just have the absolute value signs and then just to the power of n. Anyway, so this is all fine and dandy. This reason why this works is because, well, let's say if I plug in n equals 1, and I guess I would need a less than or equal sign here. If I plug in n is equal to 1, then they're equal. If I plug in n is equal to 2, well, it's only half of whatever this is. So this one has to be less. So if I plug in 3, etc., 4, 5, all the way to infinity, this is always going to work, right? So I can say for n greater than or equal to 1, this will be true. Well, this now means that if I take the sum, this has to be true. And remember, I'm taking the absolute value here because if I can prove that this converges, then without the absolute value sign, it has to converge. Or more importantly, let's say if I had the negative 1 at the end here instead, it has to converge. So that's why I'm doing this. And remember, this is the whole, if your series converges absolutely, then your original series has to converge. So this is one of the things we talked about. And if I finish filling this out, I'm going to get this. And I'm still writing the unnecessary brackets. Anyway, the point is, we know when this will converge, right? This is just your geometric series to the power of n. Well, this will converge whenever this is true, right? We need this to be strictly less than 1. All right. So if I take this and I do some rearranging, then I get less than 2. So here we get that x is between negative 4 and 0. Right, I plug in negative 4, I get negative 2. Absolute value, I get back 2. 0, I plug in 0. Absolute value of 2 is just 2 again. So basically, if I know x is between negative 4 and 0, well, this converges, and therefore, since this converges, this is trapped in between, right? Let's say 0 is less than my sum, which is less than or equal to some number. Let's say if it's 6, my sum is trapped between 0 and 6, so it can't blow off to infinity. That's the whole point here. Great. So we know n equals 1 to infinity this here converges for negative 4 to x to 0. Great. So that's a good start. Because we know it converges absolutely, our original sum also has to converge on these points. Right, also has to converge in these points. So what was our original sum? This was our original sum. Also converges. for -4 less than x less than 0. Remember, this is the whole thing that says if our sum converges absolutely, our original sum has to converge. And remember, if I just plop on absolute value signs here and here, well, it gets rid of the -1 to the n, and I still have the same thing here. Great. So we know the sum will converge for -4 to 0 for the values of x. So what does this tell us about So what does this tell us about outside this interval? Well, if we go up a little bit, back to what we had originally, we know that if this here is not less than 1, right? If I take the absolute value sign here, this is not less than 1, then we know it diverges, right? It's not less than, if it's like bigger than 1, then it diverges, right? So, like for example, I plugged in 4 the first time, it diverges. If I plug in 6, it'll diverge. So basically, if I'm outside of 1, then I don't know what happens. Then I know for sure my series diverges. Well, what if we take a look at the actual endpoints themselves? So this is where it gets kind of tricky. Often when you do these arguments, you can tell between what numbers it might converge, but you're not necessarily sure on the endpoints. And here, I'll show you why. So let's test x to be -4. Let's say x is -4. I plug it into my series here, and I get the sum of n equals 1 to infinity -1 to the n over n. -4 plus -2, well, that's -2. -2 over -2 is -1. Right. So here I've got -1 to the n times -1 to the n. Well, this gives me n equals 1 to infinity -1 to the n plus n, right? So it's 2n. Remember, you add the exponents as long as whatever you're multiplying are the same. Over n, and of course, -1 to the 2n. Let's see what happens. I plug in 1. It's still even up here. 2, even. 3, even. It's always even. So this leaves me with 1 over n, right? Because -1 to anything even gives me back 1. So this, we know, diverges. It's the p-series for p equals to 1. Great. So we know it doesn't converge for -4. But what if we take a look at the case of x equals 0? X equals 0. So we've got -1 to the n over n just like before. And if I go back up here and I plug in 0, 0 plus 2 gives me 2, 2 over 2 gives me 1, times 1 to the n. Right? 1 to the n is always, well, 1. This is equal to n equals 1 to infinity of -1 to the n over n. So this may look very familiar. This is, in fact, the alternating harmonic series. So, what do we know about this series? Well, it converges, right? You can apply the alternating series test. Use AST. Alternating series test, and, right, so my signs, or sorry, the signs for my terms will alternate. We know it's decreasing, and we know 1 over n will go to 0 as n goes to infinity. So it converges. So that's kind of wacky. Based on this other stuff, you know how in our original series we had divided by n? Well, the thing here is this divided by n actually helped it converge at x equals 0. So you always have to check your endpoints as well, just to make sure that you find out if they converge or diverge. Of course, I'm going through a lot more detail than you may need to, just to convince yourself or just to convince whoever's marking your paper, but it is still a worthwhile exercise to check the endpoints. So we know that it converges at 0, but not at -4. So the interval of convergence is what we found out earlier about the geometric series part, you know, the one where we did the direct comparison test, this thing here, right? So it converges from -4 to 0. Oh, convergence. It's -4 to x to 0, but after checking the endpoints, we know it diverges for -4, but it converges for x equals 0. So this would actually be the correct answer. This doesn't affect our radius of convergence. Our radius of convergence is still the same thing, right? It would be the length of this interval, which is still 4, divided by 2, which gives me back 2. So the radius of convergence is 2. So in this video, we used direct comparison test to actually find the interval of convergence and the radius of convergence. The key point you need to remember is you need to check the endpoints. So this concludes, I guess, what would be considered a good solution or a full solution. I'm just going to quickly show you how to do this using ratio test, because you could have done it, again, using ratio test. Right, so remember, we've got, and if you understand it with comparison tests and you're happy with that, feel free to stop the video now and move on with your life and do something else. Right, so this was our original series, and this is using ratio test. Right, same deal, an plus 1 over an. This is equal to, so we would have 1 over n plus 1 times x plus 2 over 2 to the n plus 1 over 1 over n x plus 2 over 2 to the n. And I suppose you could have just done this as an exercise to test yourself. So if you want something to try and check back with later, just turn off the video and skip to the end. But for now, I'm just going to keep on trucking. So this is equal to 1 n plus 1 times n, right? So remember, this is like 1 over n plus 1, and the n comes up on the top, times, and then you can just subtract the exponents, right? It's dividing, so you subtract the exponents. So x plus 2 over 2, n plus 1 minus n gives me back 1, so I'm just not going to write it, just 1. And of course, don't forget your absolute value signs. So we take the limit as n goes to infinity of n over n plus 1 times x plus 2 over 2. So as n goes to infinity, this here just becomes 1. Right? What's going on here, as n gets really big, this 1 is not really going to matter. So it's kind of like a billion over a billion and 1. Right? So this is going to go to 1. So in other words, if I want this to converge, then I need this to be less than 1. Right? So if this is true, then we have it converges. And in fact, if my explanation earlier about the convergence and when testing the endpoint was a little confusing, here's another way you can think of it. You've got x plus 2 over 2 is less than 1. If this is true, then it converges, right? And this is what translates to -4 less than x less than 0. And we just took a look at that already. We've done this calculation already. If it's bigger than 1, right? So if x plus 2 over 2 is bigger than 1, then it diverges. And this is just the case where we're outside of this interval, right? If x is less than -4 and x is bigger than 0, so then we know it diverges, right? So it's obviously not in our interval of convergence. Whoops, that's a little bit too low. And if it's equal to 1, we don't actually know, right? So let's say it's equal to 1. Equal to 1, and of course I solve this, it's going to give me x is -4 and x is equal to 0. So ratio test tells us nothing in the case that x is equal to -4 and x is equal to 0. So, of course, now you have to go back and check the endpoints, right? You have to check -4 and check -0. Obviously, I'm not going to do it here because it's the exact same calculation that we had up here, right? X is -4, it diverges. X is 0, it converges. So that's why we need to also check the endpoints if you just want to use ratio test. But yeah, so quite often in most of these cases, if you find a certain interval of convergence, you're going to likely need to check the endpoints as well, just to make sure you know what's happening at the endpoints. Right, so this is me doing it with ratio test. Awesome. Hopefully this gives you more insight. If there's a certain example you want to see, and it's not too difficult to do. By difficult, I mean, I guess, harder than the ones on your assignment. And of course, I won't do the ones on your assignment, but just give me a heads up and I could try to solve this for you and try to give you some insight on how to do this stuff. So anyway, feedback is always welcome. So either, I guess, leave a comment or send me an email. Sounds good. All right, see you later.